So number 1 on lesson 3 and 4. We have which of the following could describe the blocks in step 6 of this pattern. So for this one, you would probably be best off counting the number of squares in each step. We could just continue the pattern. So how many squares are there in step 1? How many in step 2? How many in step 3? And what are we noticing? Not exponential, because exponential would be multiplying by the same amount each time. Okay, what's the other thing? Okay, it is quadratic, but why? What are 1, 4, and 9? What are they? So that's not what I'm looking for. These are examples of perfect squares. Good. A lot of math teachers will say to at least memorize your first 12 perfect squares. Here's the first 3. All right, so this is 1 squared, this is 2 squared, this is 3 squared. What's 4 squared? Remember, exponents tell you to multiply the base by itself that many times. So 4 squared is 5 squared is 25. 6 squared is, and that is my step 6. I should have 36 squares. But the way that they're sorted, it looks like all that they're doing is taking like the bottom left square and moving it toward the top. And then it makes a perfect square if you move it back. So the one that would best match 36, which is moving the 1 all the way to the top right, would be a 6 by 6 block. So they're all making a square in this example. So you're down between these 2 options. So it's either with the lower left corner block move to the upper right corner, or an additional block in the upper right corner. What do you guys think? So they're moving the lower left block to the right corner. That's what was going on in this pattern. They're not putting an additional one. Additional would imply that there's a box here already, and they're just adding one, and that's not what they're doing. So questions on this one, does that make sense? Questions on others from any practice, anything that we're still not moving at? Deanna? Okay, so question 2 on lesson 3, 4. We have how many small squares are there in step 4 and then in step 15? So in the previous example, we were able to just continue the pattern because it wasn't that many steps ahead that they were wanting. Since it's going all the way to step 15, I'm not necessarily going to want to continue the pattern that many times. So step 4 we had from the last example. How many squares would there be in step 4? Remember, there was 1 here, 4 here, 9 here. What's the next perfect square? So there should be 16 in step 4. Now step 15, I think I'd rather make an equation. So like, what did you do each time? You squared the step number. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. What is 15 squared? No way, it would be way bigger. Okay, good, that sounds better. And let me just go type and make sure that the key is right, although, yeah, if it's like way more steps than it is to just continue the pattern, you'll definitely want to make an expression or equation that represents it. And those are right, that's the answers for that one.
Okay, so good on this one? 16 and 225. Okay, other questions from any part? Eli C? Number 9 on this one, we're on lesson 3 and 4, if anyone's lagging behind. Okay, so this one's a good one it's a good test question. Each figure is composed of large squares and small squares. The side length of the large square is X. So we're gonna write an expression for the area of the shaded parts of each figure. Now, these are all squares. So how do you find the area of a square? That works. And then what do we know about squares specifically? They all have the same side lengths. So you could write it as length times width, or if we're talking about a square, it would just be side length squared, because that would be the same thing, because it'd be the same number times the same number. And we want just for the shaded parts. So like where I have this large square, it told me in the instructions, the area of the side length of the large square is X, which means that this side is also X. So for figure A, my large square is X times X, which is what? Think of our exponent rules. X to the first times X to the first. So not just be X. Or think about it in this respect. If my side length is X, then my area is gonna be X squared. All right, also an exponent rule. If I have X to the first times X to the first, we add the X. So that's my large square. We want just the shaded parts though. So they have some non-shaded squares inside of it. Would that add or subtract to the area of the shaded part? So it's gonna be X squared minus, and then I need to find these areas, which I could because they have dimensions. So if area of a square is side length squared, what's 1 squared? What's the area of one of these little squares? 1, right? Because 1 squared is 1. And I have 4 of them, so 4 times 1, which is 4, and I'll simplify it, because I'm sure it doesn't have 4 times 1 in my answers. But that's like basically what you're doing, is you're making an expression based on what you're given. And like use your critical thinking skills. If I have these non-shaded parts there, that subtracts from the shaded area. 4 times 1. Now the other one. Keep in mind, they're considering these as the large squares. So they told us earlier that the side length of the large square in each diagram is X. So I have X times X, what's my area of this first square? X squared, and I happen to have 2 of them. So I can write that an expression down here. I have 2 areas of X squared. Then we have these little squares connected to it that are also shaded. So does that add or subtract from the total shaded area? So you'll put a plus. Sorry, I know it's like really jumbled. I'll try to write it over here. 2x squared plus the area of these little squares, which they have the dimensions there. So if it's a 2 by 2 square, then what's my area? And I have 2 of them. So it is 8. It's 2 times 4, which is 8. So now see that we have those options. 2x squared plus 8. Right. And they are.
You'll have something similar on your unit test too. Yes. Yes. Right, questions on this problem? Questions on others? David? Number 8 on this practice. Okay. So we have at what whole number for x is 3 times 2 to the x greater than 3x squared plus 2x. So you have a few options for problems like this. The one that I think would be easiest is to make a table for both. So my inputs would be whole numbers. It wants to know at what whole number is this, what do we call this type of function? Is it linear, exponential, or quadratic? It's exponential because the variable is the exponent itself. And then we're gonna compare it to this other function. 3x squared plus 2x, what type of function is this one? It is quadratic. Because it has an x squared in it, and there's nothing higher, like there's not an x cubed or an x to the fourth. So that is quadratic. Now, you have a few options, like you could also graph it and try to see, but I do think the whole numbers, like whole numbers would be positive and whole numbers, like non-decimals. So, and also whole numbers, I think include zeros, we can try to do zero too. And then 0, 2, 4, 5. I'm gonna use the calculator. I'll show you the calculator. So I made a table to organize my info, but we're trying to keep track at what whole number for x is 3 squared x greater than this one. So I'm gonna go to my calculator now. So 3 times 2 to the x, which we'll just start plugging in whole numbers. And then the other one was 3x squared. And then I want to say plus 2x. I think run this part. 3 times 2 to the x and 3x squared plus 2x. Okay. So let me remind you of what my expressions were. All I did was change the x in each expression, so everyone see that? Whenever you plug in values into an expression, you should use parentheses. Otherwise, you could get a wrong answer. The calculator doesn't read things properly unless you always put that. I'll even put parentheses around this one so that I'm following my own instructions. So it says, at what whole number is this one greater than the other one? Let's see. So I guess it's not counting 0 as a whole number because 0 is not the answer. So let's start at 1. So right now we have, that's weird. Okay. So I would say that the answer could be 1, but it's not 1 on the key because it's already greater than the other one, if you can see that. But what my key is showing me is that when I plug in 2,
All right, the exponential is less than when I plug in 3. The exponential is still less than when I plug in 4. The exponential is still less than. But then when I plug in 5, oh, oops, I'm switching the wrong number. Hold on. When I plug in 5, the exponential overtakes the other one. So it wants the answer to be 5, but really I would accept 0 or 1. I'll probably have to add that in because at 0 and 1, it does start to be where the exponential is higher. So it's just a badly worded question. I'll probably remove it in future algebra classes. But here's the 2 graphs. Maybe this shows you better for this one. It doesn't want like here necessarily where it's greater, the exponential. It wants it more so up here where the exponential in the red is always higher than the other one. So yeah, I will accept the other answers if you put 0 or 1, but it does want the answer 5 when you type it in. So let me edit that right now. So we have the table shows the values of the expressions 10x squared and 2x. Describe how the values of each expression changes as x increases. So we're filling in the blanks. 10x squared grows by blank amounts. So would you say that is 10x squared increasing or decreasing as time goes on? Okay, it's increasing amounts, but by blank growth factors. So, my growth factor from 10 to 40, like, because factors are things you multiply by. I would have to multiply what number by 10 to get 40? And I'd have to multiply what number by 40 to get 90? So I did 90 divided by 40. So timesing by 2.25 would give me from 40 to 90. From 90 to 160, so I'm going to do 160 divided by 90. It's like 1.7 repeating. I'll round it to this. So these growth factors, would you say that these are increasing or decreasing? So that will be decreasing growth factors each time as x increases by 1. For the other expression, the 2 to the x power is changing either exponentially or linearly. What do you guys think? And if it's exponential, what is it multiplying by each time? How can I go from 2 to 4? How can I go from 4 to 8? Timesing by 2, and then it's consistent throughout. So I agree, this one is exponential. And it blank doubles or halves. Which one do you guys think? And then that's how you fill that out, so that it's completely right. Does that make sense? So really, it's just like vocabulary. Remember that factors are things that you multiply. So this one, I think the tricky part was figuring out what the growth factors are. But you always could by taking a number and dividing it by its previous number. And that's how you can compare these. Good on this one? All right, any others? Yeah. All right. So we're writing an equation to represent the relationship between
the step number N, and the number of squares Y in each step. So this is the one where we figured out the pattern was doing what each time? It was squaring the step number. So if my step number is supposed to be N, it's gonna be N squared equals, they said Y is the number of squares. So it should give you probably two ways that you could put it in. It should give you points if you write it like this. Or like this. So let me see if it cares. Hopefully it already gave the answers or points for both. Okay, so you can do it with the Y first, and you can do it with the N squared first. It should give you points either. Right, so don't like let those trick you. You're able to do it when it's numbers. But then when they want you to make an equation, that always like trips people up. So just think of the math that we did and apply variables in the right spots. Questions on that? Questions on others? We have 7 minutes left. So if you have a question, feel free, or if you need another attempt on something, you know.